Okay, so yep, I think is 9 o'clock. Great. So welcome back to the NLP class. And I think before I think today we don't have too much announcement. I think the first announcement is probably tomorrow is the last day for submission. Who have already finished the assignment? Yay, raise your hand. Hey, we got one. How are you doing today? Okay, great. So spend all your time you need, right? And enjoy, all right? And last week, there are still a lot of people, like 5 to 10 students asked me, where can they get the slides, where the YouTube, where the GitHub, they cannot access. So this is the last time I'm gonna talk about it. That is, you just simply type my name.com, to scroll down, and there's a natural language processing. You can click on the slides to access all the PowerPoint, Google Slides that I use, GitHub. Yeah, go to my GitHub and don't forget to give me stars or something like that, right? I would really appreciate it. And go to the YouTube, click some like, all right? So that's it, right? But yeah, YouTube is not, my purpose is not really to be a YouTuber because I don't think I am that type of person, but mainly I want to delegate YouTube to help me teach you guys coding in a streaming fashion, right? Great. Okay, so without further ado, why not we come to uh, the lecture right away, all right? So today's lecture is, so last Monday we talked about recurrent neural network and language models, and that would be your assignment, right? A2. And hopefully you guys enjoyed the Harry Potter. I think, what do you guys think? For A1, how about we rank the difficulty for A1? Who feel is, okay, so we have very easy, medium, difficult, and very difficult, okay? Who think is very easy? Okay, who think is easy? Who think is intermediate? Okay, who think is difficult? Who think is damn very difficult? Okay, good. Okay, great. So yeah, okay, so I thank you for your response. So I and Gan can play around with assignments and try to make sure that it's around intermediate, all right? Because we, based on psychology, the maximum performance of a human is achieved when you get some task that is just slightly challenging above than your skill, right? That is when humans reach the state of flow, and then you can exhibit the maximum performance. So we understand that, and we will achieve that. Okay, great. So without further ado, let's go to our 4 lectures of the week, not of the week, of the course, and that is a long short-term memory, all right? So long short-term memory is, okay, so let's a little bit preview before I go to my boring slide. So we have learned about recurrent neural network, right? Neural network, right? And I mean, recurrent neural network basically can do everything, right, that you want. Last time we talked about language model, right? But I also told you that using recurrent neural network, we can do name entity recognition, part of speech recognition, classification, sentiment analysis, even question answering. You can do basically everything, right? So now I'm talking about the vanilla, right? Vanilla one, right? The classic one, like the very basic one, right? In which basically we have something like this, right? And this is the input 1, input 2, input 3, right? So that is a recurrent neural network. And but now there's some problem, right? And for those who already studied my machine learning class, actually I hinted already, right? But I don't expect you to fully understand. because I know that if you don't understand at first semester, I will say it again on second semester. Hopefully, your brain is already prepare all the neurons to understand myself. Oh, my sound is nice. Yeah. So so there's a big problem of long-term dependencies, right? So what do I mean by long-term dependencies? All right, I have problem with English. Okay, long-term dependencies, and I think you guys can see that, right? That in this whole network, there's a WH and WE, right? Correct. There's a 2W that we try to learn, two-way matrix, right? And that's it. And we reuse, basically, we reuse this two matrix, right? Over and over again. And basically that's it, right? And how long we can go? Infinite length. Infinite length. Right? Infinite length. So, but in theory, it's infinite length because you can keep multiplying forever, right? And you can do infinite length. But in practice, no. All right. In practice, probably I don't know in recurrent neural network how much, but in eventually, if you go to certain length, it will forget the beginning, right? Right, because it's just way too long, and you multiply it so many times such that it forget the beginning, right? Right. So this is a big problem, right? So that is forget the past. I mean, not the past, the very long past. Is that the right English? But I'm not sure. Yep. Forget the very long past. Right. So that is probably one of the biggest problem, right? Now, the second big problem of recurrent neural network is vanishing gradients. So I think you guys already see, right, that if we have many like this, every time we go to the next edge, we have some computation, right? And let's say we do this 50 times. Let's say 50 times. 50 times. If we do this 50 times, when we backpropagate, we have to take the gradient of this, multiply with all the things in front, right? Based on the chain rule to compute the gradient, correct? So if we have 50 times, then probably we roughly 50 multiplications, right? That we have to make. And you can imagine that if some of this number, let's say the gradient here is 0.1, and this is 0.2, and this is 0.2, it happens sometimes that your gradient is like less than 1. Okay, it's not, yeah, less than 1. Then when they multiply together, they become very small, right? They become super small, right? So this effect is very prominent, especially for the front guy. Because for the front guy, you need to do many you have to do a lot of steps here until you get the final loss, right? Right, in which the final loss is basically usually in this form, right? Right, for linear, for regression, or for basically for cross entropy is basically probably something like this, right? This is cross entropy loss. But anyway, we don't care about the loss, right? Here we are trying to say that we compute the loss after 50 times, but the vanishing gradient is very prominent for the first guy, because if I want to know how much I need to change myself, right, based on the loss, I have to compute the chain, right? How much this guy respect to this guy, and then how much this guy respect to this guy, how much this guy respect to this guy, right? And then do the chain rule, remember? Right? Do. Eventually, you multiply so much, the gradient to update this guy probably will be like so small that this guy won't change, right? Eventually, right? So you can see that vanishing gradient is a big problem, especially for the front guy, right? If you can see that vanishing gradient is a problem, oh, by the way, vanishing gradient happens when your gradient is less than 1, right? That if you don't see that, that is a very clear way. But associated problem is exploding gradients, right? Because if you have so many layers, right? I mean, so many H, and you can imagine that if the gradient, each of them is greater than 1, what will happen? They will just multiply, blah, 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 blah. Maybe this, you can imagine this 50 times, right? Everything is more than 1. Eventually, this guy will get how big? Like 10,000 maybe, right? And that means that if you just update this guy just one step, it go 10,000, it can probably overshoot, right? So this is a big problem, right? Now, so now you can see the limitation of recurrent neural network, right? Of course, there's an associated problem that I already talked about, that is sequential, right? And this problem cannot be fixed by anything, right? You need to just move to transformer to fix that. So let us talk about each of the problems. So I already talked about sequential. That is, you have to go to transformer, right? There's no other way, right? Right. So yeah, sorry. Today the topic is LSTM, but even else can solve that problem, right? But how about exploding gradient? Well, exploding gradient is nothing related to LSTM. In exploding gradient is super easy to fix. You just say if the gradient is more than 5, you cap it, finish. You don't need to do anything. If let's say the gradient here is 5, 10, and then 5 times 10 is 50, you just cap this to 5. You understand? You make it the gradient as big, the biggest possible is 5. Because when you update, you only update the direction, right? Of course, 50 is the magnitude, like you want to go to that direction opposite of this 50 units. But I would say, no, I don't want to overshoot that, right? So I just cap that to some number, right? So that is a very, very simple idea to fix this exploding gradient. A vanishing gradient is difficult. Vanishing gradient is difficult because this number is 0, let's say 0 0.3, 0 0.2, right? You cannot cap that, right? You mean it cannot be less than 1. No, we cannot do that, right? So we have to think about how do we do this, right? And so this is a big problem, right? So this is simple problem, very simple. Number 4 is a problem that this guy will never be able to solve, so we don't talk about it. Number 4. Number 2 is something recurrent neural network we have to think about. Number 1 also we have to think about, right? How to fix the recurrent neural network. I mean, I'm talking about the vanilla. So now, based on these 2 problems, today what we're gonna study is something called long short-term memory, right? Long short-term memory, right? So of course I haven't even shown you the equation how to fix this, but by the way, it does not really fix it. Okay, disclaimer, but it fixed to a certain extent. But I'm gonna talk like a few things before I jump my preview. So basically, the idea is you add extra parameter. That's it. That's the only idea. So I already told you, right, that in recurrent neural network, we only have WH and WE, right? Which are continuously multiplied, correct? And eventually, when you multiply so many times, it lost the beginning, right? Very, very easy to fix. I mean, you can mitigate, not fix. Very, very easy. You just add one more extra parameter. Say that maybe you also have some called WC somewhere, and this WC is not multiplied that many times. Understood? And maybe WC is a product of something, right? I did not introduce the equation yet, all right? It's just the philosophy first. That is, if you add a parameter and this parameter is not multiplied that many times, then eventually you can preserve longer length, right? So that is like the only concept of LSTM, right? You may say that then, Chucky, why we have such a weird name, long short-term memory? Well, in recurrent neural network, you only have WE and WH, right? By introducing another parameter, some W, which we don't know yet what are this W, maybe that can be represented by how our brain works. That is, we have long-term memory that can keep memory from long-term, like 5-10 years ago, right? So that is basically how the names come. But actually, mathematically, it's nothing about brain. It's nothing about thing. It just add an extra W. That's it. That's it. So the idea is very, very simple. The last preview I will give before I move on the real slides, and that is, does LSTM really fix the long-term dependency problem? What do you think? And the answer is no, right? No, because okay, the original problem is that WE and WH got multiplied so many times that it lost the beginning, right? Oh, no problem. I add more W. This W will not be multiplied that many times, or maybe it can keep some information from the beginning better than this WE. I can keep adding W, right? Add more W. I can add many W, and this W maybe multiply with X and H and have some interaction, and basically I just manipulate so that we have extra parameters, right? But there's one point in which, because this W that you add, it will still be multiplied many times, right? Right? So there will be a limit, right? That it will still forget the past. The question is, how much long-term, short-term memory or LSTM can keep? And there's a paper, actually later on, like lecture 16, I will talk about it, but I can already talk to you that it can preserve 50 steps. Yeah, 50 steps. So what do I mean by 50 steps? 50 steps means that if I have a sentence, imagine like this. If I have a sentence, I have 50 words, right? Blah, 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 50 words. And I want to predict the next word. And this is the last word it can use the information from here, right? If you want to predict the 51 word, you will never know this. No, you will not know that, right? So that is what I'm trying to say, that the meaning of long-term dependencies, right? So this is like theoretically, LSTM can only look back 50 steps. How about transformer? I don't want to talk too much about this guy because we're going to talk about eventually, but you may say that, Chucky, I don't really understand long-term dependencies very clearly. Can you give me one example? Well, very good. Do you know code generation? Code generation. To generate code, I have to write a very long code, right? And in order to write the code in here, there must be a relationship between this part and that in the beginning, right? In which I import some library, right? So if your model cannot understand long-term dependencies, code generation, such tasks cannot be achieved, right? So you can see that long-term dependency is a very crucial thing. All right. So yeah, hopefully that is a crash course, 10 minutes preview, LSTM / whatever. Yeah. So that is the preview. All right. If you don't understand anything, actually what I said, everything is in the slide. All right. But I just previewed and make you guys understand in one go. All right. So let's talk about LSTM. So where are we? So now we are at right here. Right, LSTM. So the first thing we have already talked about is vanishing gradients. And basically, this is what we have mentioned. That is, imagine that we have several layers, and the gradients of the first guy is basically using the chain rule, we need to multiply several gradient, right, to obtain the one gradient, right? So imagine that if we have 50 or 100 of this thing, then this can be cause a lot of our gradients to either vanish or explode. And for those who don't like mathematics and you don't understand, like, Chucky, why you teach me so many things like that, then I give you this kind of task. And I won't read it out, right? Okay, I should read it out. When she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy something, blah, blah, blah. After installing the toner, she finally printed her what? What is the answer? Document? You tickets, right? Yeah. You, human being, has very long-term dependency. See, you can look back and see its ticket. Computer cannot do that if you don't provide them very good way. If you only use RN, it cannot say ticket because it can maybe only look back 5 steps or 10 steps. You understand? Because why? Because of the vanishing gradient, and also you multiply many times. Okay, so that is a very big idea about this. This long-term dependency problem is also related to grammar, right? So for example, the writer of the book is, right? The writer of the books are. Should be are or is, right? So you can see that if your neural network cannot look back certain steps, you can see that there will be some problem with your whatever language model or grammatical models, right? So this is another examples why it matters a lot. So exploding gradients, right? Of course, we talk about vanishing gradient. Exploding gradient is also very possible, right? And in many cases, for those who have experience in PyTorch, you will see this problem, right? INF and NAND, right? Who got this problem sometimes when you train neural network? No one. Great. Yeah. Okay. Actually, a lot of people talk to me about this, but you don't raise your hand, right? But anyway, that is a problem. And I'm not going to talk about this mathematics, but it's very easy. It's basically say that if the gradient is x bigger than some threshold, you basically multiply with that number divided by the magnitude of this number, right? So for example, if you set the threshold to be 5, right, and your gradient and your gradient is like, let's say that, right? Correct. And so, and the magnitude, I'm not sure what is the magnitude here. Magnitude is probably that, right? And I don't know what is that, right? That is G hat magnitude. For those who don't know what I mean here, right? And so threshold is maybe 5, and this is actual G, right? And then you do the math, right? So that is how it, by the way, a lot of people like to say, what is 1 to 3? It's just example, okay? But I want you to understand that the gradient look like this. Why 3 number? Because you have to update for some W, right? And this is for another W, this is for another W, right? So that's why it's a vector. Yep. So yeah. But anyway, if you don't understand this, you don't have to understand this, because in PyTorch, it's only one function. It's called, if I'm not wrong, nn.utils.clip something. Okay? Don't quote me, but something like that, right? That is in the PyTorch, right? And basically, it will control your gradient to not ever explode. You should always use this whenever you use LSTM, RNN, GRU. Yeah, always. There's no reason why you don't use that. Like, no, because exploding gradient is a very common problem in all those recurrent neural network variance network. All right. So yep. So how do we fix the vanishing gradient? I already told you how about we introduce another parameter. But in NLP, a lot of people create a new name called a separate memory, all right? But memory is basically a W, right? There's not no such thing as memory in neural network, right? The only thing we have is W, and we hope that that W encapsulate and memorize information from the past, right? So don't think that how do we create this memory? Oh, we install more RAM? No, it's not related to memory. It's nothing related to RAM. It's a W, okay? So now we come to long short-term memory, right? So again, as a student of mine, I always want you guys to remember what is introduced in when, right? And LSTM is proposed in 1997, all right? And that is a good thing that you remember who actually proposed it, and it's actually Schumit Herber, right? Yeah, did I announce your name correctly? Yep, I'm sorry if I don't. But anyway, the idea is very simple. You introduce a lot of parameters to capture a lot of information. That's it, right? So I want to remind, before I show you the equation, I think I would teach this 15 minutes and I would just break. All right. This is probably the main slide of today's class. So I want you to remember what is a recurrent neural network, right? So recurrent neural network is basically the next edge, all right? The next edge is basically some activation function that we don't care, is ReLU, 10, whatever, we don't care. And then take WH, right? A weight matrix, multiply with HT minus 1, right? Plus WE and X, right? Right? And then plus B, right? So that is basically recurrent neural. Only one equation. That's it. And you will then will have many edge. Then the next edge is dependent on the previous edge. And this one is, sorry, I forgot T here, right? Yeah. Yep. And basically that's it, right? What else I have to talk about? Yep. This is a matrix. This is a vector. Matrix, a vector, a vector. Let's say small x. You guys will, right? Yep. And this is also a vector. Okay, matrix, vector, matrix, vector, vector, right? This is the activation function, right? And this is a vector, right? Yep. So basically that is recurrent neural network, nothing fancy, and you always share the WH and WE across all the T, right? Now, you can see that why vanishing gradient happens, right? Because you only have two parameters to keep the information, right? How about I say that just add more parameters, okay? And then somehow let them talk to X and keep the information. That is the only idea we have, all right? So don't be confused by, oh, Chucky, how did Schmidt-Huber in 1997 come up with this 6 equation? Nothing, trust me, it's nothing. You look at the formula and you say nothing, right? And he did, I don't think this guy understands human being also, right? It's purely equations, right? So firstly, we got this something called forget gate, right? And I don't want you guys to confuse what is forget gate for now, right? But you have to understand what is this firstly. So basically, we define a WL, right? And multiply with this HT minus 1, okay? Look very similar, right? And then UF multiply with XT plus, this is basically the same thing with what we see, right? But one thing we don't see is a sigmoid function, right? It's a sigmoid function. So when it's sigmoid function, this guy is all vectors of numbers between 0 to 1. Understood? Not 0, 1. The values between 0 and 1, okay? Because sigmoid do that. Yep. So you can imagine this guy can be something like 0.2, 0.3, 0.01. 0.9, blah, 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 like that, okay? So that there's no negative, right? Sigmoid don't give you negative, right? So why sigmoid? Because later on, we will use this. If we take this guy, multiply with some vector like h or something, then basically this can serve as a mass. So you can imagine that maybe I have this 0.2, 0.3, 0.01, 0.9, 0.1, 0.2, and maybe I have an actual number, like some number, like let's say some activation output, and I got 1, 2, 5, 9, 3, 2, right? Correct? You multiply this guy, multiply this guy, this guy, multiply this guy, right? So by doing this, you ask the computer what number you want to forget, which part of the parameter you want to forget, and which part you want to remember, something like that. All right. So basically, this guy is like a mass. All right. In Python, it's basically mass, right? You take one number and multiply, and basically it preserve or lower the importance, right? So that is why it's called forget get and why there's a signal, right? So this is the purpose, right? Things will get more clearer once we review all the equations, right? So that is the first thing. But you have to understand why sigma, because we want this guy to be a mass, right? To be a mass, the shape should be the same as what it mass also, right? Otherwise, it cannot be multiplied. So that is just a trivial thing. Now, the next thing we have is same thing. We call this input gate. So you can see it's like basically the same thing. But now we have WI and UI. You need to be understand that this W and this W not the same. Okay, that is why I changed the subscript, because I want you to know that this W and this W not the same W. Okay, and this U and this U also not same. You may say, Chucky, why you don't change U to W? Because it's just from my preference that I don't want you to confuse W and U. So I just want to say U is for X, okay? But U is still a weight matrix, okay? To make sure that you don't confuse. And also the B, this BI and BF also different, okay? So by introduce a lot of parameters, you allow the network to remember a lot of things, right? And this is called input gate. And this is also a mass. This is also a mass. Okay. So we have two mass full of 0 and 1 and numbers in between, right? How about the next output gate? We have one more, okay? That is deciding, this is also a mass, right? And once again, we have WO and UO. That is completely different from, we don't share the network, right? So we have three mass, all full of 0 and 1. I mean, 0 numbers between 0 to 1, right? Like a matrix like that, right? Now, how do we actually apply this mass? It's extremely simple. Firstly, we take this guy is basically recurrent neural network. You see, it's basically W times H, U times X, 10. This is basically what I already teach you right just now. That is activation function. This is recurrent neural network. You may ask me why 10? Why not ReLU? Because this guy is in 1997. So in that time, only 10. There's no ReLU, leaky ReLU. No, they only know 10. All right. So we call this. So this guy is a number. Okay. This guy is a number. And this guy is basically, we call this a new cell content, whatever, right? But one thing I want you oh, I should not use that color, right? All right. Now, one thing I need you to observe is that this and all this are same shape or not? They're in same shape or not? They are all in same shape. Yep. They are all same shape. Because they are all in same shape, I can always take FT multiply this guy, right? When I say multiply, I mean multiply, not dot product. Okay, multiply. I can do this and multiply with this guy, right? This guy multiply because they are in same shape, right? I can multiply, right? So that is something I want you to observe. Same shape. Right. Now, how do we do the next thing? We say that the actual CT, actual CT right? The actual CT is nothing but the forget gate multiplied with the previous cell state. And here, notice here, it's called Hardeman product. And you may say, what is, I should not say bad word, but what is Hardeman product, right? Hardeman product is basically element-wise multiplication, right? So it's basically multiply, not dot product. Dot product, if dot product, I don't show you the symbol, see? I just do, right? So that is my notation, but you need to see that this guy is Hardeman product, right? But I will erase because this color cannot see very well. And then I do the input gate multiply with the previous cell state. All right. So basically, well, this is the new content, right? This is the new content from XT, and this is the previous content, right? That is already accumulated from long time ago, right? And we say that, what do you want to forget from the past? And what do you want to remember for now, right? So that is the meaning. That is basically the meaning. And now you have your memory called CT. Okay, this is the actual memory, right? So again, the memory is nothing but what you want to forget from the previous content and what do you want to remember from the new content. All right, so that is CT. And finally, if we are good, then the next one is HT. So let me erase all this. So this is actually what we want, right? HT. This is the final thing, the actual thing we want. And that is HT, right? So what is HT? HT is nothing but take the output gate, Hardeman product with whatever is in the memory, right? Say that, hey, to answer this word, I will take this information from this memory, apply some 10, and OT will say what is needed to answer this using this memory, right? And that is the answer, and that is HT, right? So that is that. There's nothing. These three guys are mass, and you create a way to create new content, what to remember, what to forget, and what should be output as a HT. And this is the final output we want, right? So extremely easy. If you really truly understand simple dot product matrix multiplication, you should already understand by now, right? And you can see now that why it can fix vanishing gradient, right? Because you have so many paths, right? So many paths. You keep the information of X so many ways, right? You keep here, you keep here, you keep here, you keep here, you keep in C2, right? And you keep H. So if H forgets, C helps you remember. See? Remember? So using this way, it can preserve longer term information. But still, even you use this way, it can only preserve up to 50 steps. 50 steps. All right. Okay, great. So I think this is the LSTM, and hopefully now you listen to my 10 minutes lecture, you understand what is LSTM. All right. Great. So I think why not we after this explanation, why not we have a break? Okay, and we come back. Thank you. All right. So welcome back, and it's a miracle today. No one approached me and asked me what is LSTM, and so probably I did a good job explaining, I hope, right? But anyway, basically you add more W and it will fix a little bit. I don't want to say fix it, mitigate, right? Great. So I think this is the main slide, and I don't have anything else that I want to really focus to teach you today. But the rest of the slide is just for maybe like just for sightseeing, okay? Not so important. So we can go quickly and then we go to the code. This guy is blocking. Go back, go. Okay, great. So I think I will not talk this. How does LSTM make it easier? So I already say something that is you add more parameters, then it can solve a vanishing gradients. And of course, in 2013 to 2015, LSTM is the main model, right? Usually you guys are in high school, right? In 2013, 15, right? High school, elementary, right? Yeah, I'm in my PhD at this time, right? So yeah, during my PhD, everyone is talking about LSTM. My professor always talk, Chucky, you need to use LSTM for your thesis, okay? Yes, okay. And then I tried to study LSTM for a whole month and I still don't understand. But anyway, yeah, LSTM is very popular in this day. But yeah, after 2015, Transformer comes in 2017, and no, since then no one used LSTM for now. But if you understand LSTM, it's good. That's a good foundations for your life. Great. So there's also one thing called GRU, and it's LSTM in 1997, and then we have GRU 2014, and don't be fooled by this name called gated. Okay, by the way, GRU stand for gated recurrent unit. Gated recurrent unit. And don't be fooled at Chucky. Oh no, this guy is another guy. It's not the same as LSTM and IN. Then what? If you understand LSTM, this guy is like so easy. It also add parameter, but not add as many parameters like LSTM. That's it. Simple as that, right? So if you understand my LSTM slide, you understand that this guy just want to add less parameter, and he proposed it called to GRU. By the way, this guy better or LSTM better? In short, just use LSTM. They are basically the same performance. And nowadays GPU is so fast, so we don't care which one we use. So everyone use LSTM and less people talk about GRU. So yeah, so I will just go quickly. Yep, I go too quickly. Yes. So basically, instead of forget gate, input gate, output gate, now they have something called update gate, reset gate. Don't be fooled by this term, okay? It's basically just the same equation, right? But just change the name, and then instead of the cell state, now you have the previous state called h tilde-t, and then you do something with it, okay? So basically, it's the same idea, but less parameter by like 2, 3. I think you reduce by like half parameters, I think. That's is sometimes good. PyTorch and n.gru, just one line. You can get this done. So which one you want to use? Rule of thumb, start with LSTM. And you can switch to GRU, but I never see people use GRU nowadays. Like if I am teacher, I will teach you only LSTM. Because if you understand LSTM, GRU is so easy to understand. It's the same. Just add less parameter. Now, direction. There's a lot of variants, right, of this LSTM or recurrent neural network, right? That is, you can go one direction, right? Previously, I teach you one direction, right? So this edge move forward, this edge move forward, right? But when I want to say the movie was terribly exciting, good or bad? Good, right? Because it's terribly exciting. But because you move forward, this guy never know the future word. Maybe this guy will give a negative response. And when you average them, maybe this guy will give negative, simply because this guy don't know the future word, right? So how do we do? Well, you go forward, you get five hidden states. You also go backward. You have another H, right? And completely another set of W. Okay, I will say again. For the forward, you have W, H, and W, E, right? Correct? For the forward. But for the backward, you can also do another backward. And this one, you have another, let's say tilde, okay? To mean that this guy not the same, okay? And for going back, you also have another one called, okay, let's say tilde, okay? I don't know what to say, okay? So the forward function has 2 parameters, go back also 2 parameters, okay? So by doing that, you can have 5. Forward, you have 5 here. Backward, you also have 5. Then you just average all of them into one, you will define positive. Then it will be more accurate because you read from front to back and back to front and average all them together, you'll probably get a better results, right? So that was probably a very quick idea why bidirectionality. Should we always use? Answer is always do. I don't see any task in which you don't want bidirectionality. I don't see why, right? Yeah, so I think in PyTorch, you should always say bidirectional equal to true, right? Okay, maybe there's one case you don't want to use bidirectional that is your computer's burn, something like that. Your computer's fan is spinning so hard and it's so noisy, you may want to turn off, right? Because when you use bidirectionality, you multiply your parameters by 2, right? Because you have like 2 things like it. So but that is probably the only reason. So. But I found that you guys' computers are very strong, actually. Yeah. So yeah, this is basically like some kind of notations. You have uh, you have uh, uh, you have forward hidden state. You have backward hidden states, and then you concatenate. This guy means concatenate. Concatenate. Okay, this is a math notations for concatenation. And then once you concat them, you will have this, right? And this is basically in the previous one is a 10 vectors, right? 10 of them all concat together here. That would be probably, yeah. Great. So that is bidirectional. And yeah, bidirectional is a very important ideas. And later on, I will teach you something called a bird. And a bird also have this kind of idea called bidirectionality. And of course, there's a name called stack RNN. And for those who are not comfortable with this name, the reason why I mentioned this name is because when you read Medium or YouTube or papers, they'll use this word stack, but you may think, oh, novel. But actually, stack is basically multi-layer. Okay, so you can imagine that you can do only one layer, right? But then you can pass this guy up to another W. So this guy have WE and WH, right? Who told you you can only do one? You can send this H1 to here, right? And treat this H1 as X, right? And you do here another, okay, let's say this is WH1 and WE1. You can create here WE2 and WE2. H2, right? And this H1 multiplied with this WE2, and WH2 multiplied with some H0 of this guy, right? And this one has also its own H0. And then you can do many layer, and finally, you can use this very last hidden state and send to some linear layer, right? Or fully connected, whatever you want to call, and then do the prediction, right? So this can be done. You may wonder, like, why do we need so many layers, right? You can imagine that maybe the cat, I'm not sure how to explain. Basically, this guy encapsulate information from the past, right? And this guy encapsulate information from two, right? So when you do this guy to this guy, basically you take two of this guy connected to three of this guy, something like that, right? It's a little bit confusing, but basically the feeling is like by stacking a lot of layers, you allow the model to understand complex relationship. So if you have only one layer, maybe you only understand each of the word, right? Each of the word. But once you have two layer, maybe this guy actually represent, okay, let me delete this, getting messy. This guy actually represent the information from these two guys, am I right? Right? So, and this guy, okay, this guy is only itself, but this guy know this guy, right? Right? So you can see that by stacking layers, you're trying to understand complex relationship, not only single word, but multiple words. And this one will be even more. And then this guy will know a lot of complex relationship between these two and this three. You may say, what do you mean by complex relationship, like phrases, entities, correct? Right? It will automatically create those kind of relationship that these two words together means this, something like that. Okay? So stacking layers allow us to learn those complex relationships. Yep. And in 2017 paper, this guy found that 2 to 4 layers is good for machine translations, right? So that is what he found, right? So yeah, multi-layers is good. Usually, I will always start with one layer, and then if it doesn't work, I try two, and if I try four, and if all the performance are the same, I will just use one. But if adding layers helps, I will always add layers. Yep. So that is probably my practical way of approaching this idea. Great. And okay, transformer has like 24. We're gonna talk about transformer later on. Okay, and okay, I have one more slide, but I think this is not the last slide. Okay, there's one more slide because I talk very fast because I want to go to the code. But summary for those who are sleeping, you now can wake up. I know it's boring, but I think it's useful. So LSTM are very powerful. Used bidirectionality always. Multi-layer is good, but use skip connection. We did not talk about skip connection too much. I will talk about it when we talk about transform. All right, very, very important idea. In ResNet, in transformer, we all use skip connection. By the way, I know I did not teach you computer vision like ResNet, AlexNet, InceptionNet, Vision Transformer. So I will have a class in which I teach you everything from the background, including AlexNet, VisionNet, blah, 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 ResNet, and then Vision Transformer. Okay? And so we will have that class for you. And then, clip your gradients, use skip connections almost always, and you will see in Transformer. Yep. So those are the summary. All right. Hopefully you understand LSTM. Now, like I said, if you only look at me and listen to me, you only understand 20%, right? So I think I want to enhance maybe up to 30%, and then you can go back to code, and then you probably by then understand everything I teach you. By the way, did I record my video? Okay, great. Now, do you guys remember that most of the time you use nn.lstm, right? Correct? You guys keep using it, okay? Keep using nn.lstm because it's optimized and it's very nice. But have you ever wondered and have you ever frustrated like what is inside, right? Like how does it written inside, right? Here, I spent some time coding from scratch. You should never use my code as LSTM, understood? It's not optimized, it's only to show you how LSTM is internally coded, right? But in practice, you should use nn.lstm, understood? Yep. Now, if you want to know how LSTM is coded from scratch, here are the code. All right, so I will put very big, and hopefully people at the back can see. So I code vanilla LSTM for you. I have something called couple gate LSTM. I know I did not teach you, but you can always take a look. There's something called people LSTM and by LSTM. But today we only talk about vanilla is enough for your brain, right? So simple CUDA, and my input dim is 5,000. You don't have to worry like why this number, right? This is just my number, okay? So yeah, so the expected shape of LSTM input is batch size, sequence length, input dim. All right. So you may wonder like when I suddenly say this, you may probably like what is that, right? So maybe the first sentence, Chucky is eating sushi. All right. And the next word is Chucky is flying. Right. And I have many of this. Let's say this is batch 1. And I have batch 2 like this, okay? Okay. And so how do you input to the LSTM? Well, you send batch by batch, right? Batch by batch. This batch first and then the next batch. But so this batch is basically this batch. Now, sequence length. How about sequence length? Because LSTM, if you do batch by batch, for each of the batch, it should be the same length. Okay? I will say again, for each of the batch, it should be same length. Okay? So for example, in batch 1, what I can do, I take the maximum sentence in this batch. So 1, 2, 3, 4, 5, right? Then, because this guy only have 1, 2, 3, 4, and 4 is not equal to 5, right? I add just one more 0 here. Just add a padding. Okay, I call this guy is called padding. Right? And now they are equal length. I can create an LSTM that feed them in, right? Because they are equal length. How about the next batch? Do you think the next batch the length should be 5? No need, all right? The next batch can be basically take the maximum length of sentence of that batch and then do padding, okay? So that is the sequence length, right? So now that is the idea. Now how about, here, because if I want to send everything to LSTM, okay, I'm not sure whether is it better or more optimized to send this sequence length all the same across, right? So you guys can check in the code, right? But I think it can vary, I think, right? And how about the input dim? I should not use this same color. So how about input dim? Now for input dim, what is input dim? Very simple. Each of this guy is a vector, right? It's an embedding, right? Let's say this guy is 300 and this guy is also 300, right? So each of the word has a shape, has a vector, right? That represent the word. So this guy is basically that, right? So if we return this batch, so let's say we only have one batch. So this guy is 1, 5, 300, right? So this represent this guy. If I have 2 batch, then I just change this to 2. Understand? So this is the input to the LSTM. So you have to be very comfortable with this shape. So now, once you do that, you guys already understand this equation. So that I will not talk about this. This is the forget gate, input gate. I don't remember what is this. I think output gate. Yeah, this is output gate, and then CT, OT, and HT. Right. So we already learned this, right? So we're gonna skip all of this, right? But now you may wonder, like, how do we actually code from scratch? And it's actually very, very simple. So here is the magic, right? So you, again, should you copy my code? You should never use my code for your industry, whatever, right? It's just for demonstration, because some of you guys have, like, I don't know what is inside in an LSTM, right? So you can create UWB using this function called nn.parameter, right? And you just basically define the shape, right? So you can see UI is basically turn the embedding dim to hidden dim. WI is basically turn the hidden dim to hidden dim. And the B is basically hidden dim, right? So if that makes sense, right? So you have many parameters for input gate, for forget gate, for G, for open gate, right? And then finally, in the forward function, you basically, for each of the length, for T in sequence length, you take the T out of this X, right? So remember that what is X? X is basically batch size, sequence length, and what? And input dim, right? But the moment I do T here, this guy will be just one guy, right? Then this XT will become BS, not bullshit, okay? B batch size input dim. Understood? Understood? Of that T, right? So that is the input to here, right? And then you just multiply, blah, blah, blah. You see, very similar, right? Sigmoid, 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 10, 10, 10, do, and then output concat, da, 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 pop, pop, pop. Okay? So yeah, so that is a very quick demonstration of one cell, right? One cell. So this is one cell. If I'm not wrong, this is one cell. Yeah. Yeah, this is LSTM cell. So cell, what do I mean by cell? This is cell. Cell means when you go up, you hit this guy, you go, this guy is, I call cell, okay? One guy of this is this guy. Now I have so many, right? I have so many of this guy, right? So how do I combine all of this guy? Well, I have another function, hopefully, Chucky. I don't remember the Chucky before, right? So okay, I did not actually combine them, right? This is just a demonstration. How do I run this? Did I combine them here? This is basically, for those who don't know what is like peephole, it's very simple. You just change some, you just have, you just put CT here, right? So you can see that forget gate now have CT here. Why? I don't know. I just want to peep into the memory and copy some information, right? Who say you cannot, right? You can always peek into the memory and get the information, right? So that is also possible. It's called peephole LSTM. And the rest is the same. And how about couple? I don't remember what is couple. If I'm not wrong, couple is yeah, input gate. Yep. So in couple, you just change the input gate to be 1 minus forget gate. Finish. So instead of learning the input gate, you just say, if this guy is 0.5, this guy is 0.5. If this guy is 0.3, this guy is 0.7, something like that. That's that. So this is called couple errors. You may say, Chucky, so many variants. Which one is the best? No best, okay? I just want to tell you that all of this, there's no theory behind. You can play whatever you want, add any W you want. it works, it works. Okay. So you have to understand this the idea about all these creations. And yep, I think this is another cell, and again, a lot of parameters. I'm okay. I understand. Actually, I don't need the LSTM because here I just loop all the length, right? So by looping all the length, actually, I'm already connecting all the cell, right? If I'm not wrong, okay? But you can look at my code, and now you fully understand what is LSTM. But again, don't copy my code, okay? My code is not for that purpose. Yeah. Okay. I also have written two direction, right? So two direction is yeah. So basically, you have forward, backward, and basically sub-rate network. That's it. Attention, no. I will not teach you attention today because attention will be taught next week, Monday. All right. So thank you very much. I think we end early, but it's okay. So tomorrow is the deadline for the assignment, and today you will have A2. All right. A2 is very easy. Yeah. You want to say something?
When you submit the assignment, please don't try to print everything into the IP1B because when I have to check, I have to score out everything, the things that you had print, and we have 30 students. I have to check and scroll every person. So please.
Okay, great. So when you do your assignment, don't print everything. All right. Maybe if it's very long, just comment that line. Okay, and don't print. He know what you will print. Okay, he can imagine. So print only the answer. Okay, like necessary point. But anyway, great. We already have like 5 students already completing A1 by now. All right. But anyway, thank you very much, and see you next Monday. Bye bye.